Hello students, welcome to fourth lecture of S block elements. So today's first topic is anomalous properties of lithium. So anomalous behavior, that means different behavior than the rest of the others. Anomalous behavior of lithium is due to the first exceptionally small size of its atom and ion, and second high polarization power, that is charge to radius ratio. It is a strong electropositive element having very small size. So effective net effect on the other elements or with the bond, it is comparatively very strong, and as a result there is increased covalent character of lithium compounds, which is responsible for their solubility in organic solvents. Further, lithium shows diagonal relationship to the magnesium, which has been discussed subsequently. So points of difference between the lithium and other alkali metals. So first is lithium is much harder. Its melting and boiling points are higher than the other of the alkali metals. Lithium is least reactive but the strongest reducing agent among all the alkali metals. On the combustion in air, it forms mainly monoxide Li2O and the nitride Li3N, unlike the other metals. So because of very small size, it can attach with oxygen or nitrogen in multiple quantity, whereas the other elements of the alkali metals are comparatively larger in size. So oxygen or nitrogen, they are not able to attach more than one atom at a time, whereas because of very small size of lithium, multiple lithium atoms can be attached with oxygen and nitrogen. Lithium chloride is diliquescent and crystallizes as hydrate. Diliquescent, that means it is moisture absorbing or it has very good solubility. So LiCl 2H2O, it is hydrate of lithium chloride, whereas the other alkali metal chlorides do not form hydrates. Lithium hydrogen carbonate is not obtained in the solid form, while all the other elements form solid hydrogen carbonates. Lithium, unlike the other alkali metal, forms no ethanide on the reaction with ethine. Lithium nitrate, when heated, gives lithium oxide Li2O, whereas other alkali metal nitrides decomposes to give corresponding nitrite. So LiNO3 gives Li2O as a main compound, whereas NaNO3 or remaining alkali metal compounds gives NaNO2 with oxygen. Lithium chloride and lithium oxides are comparatively much less soluble in water than the corresponding compounds of the other alkali metals. And same type of anomalous behavior will be observed in each and every group's first member. And reason is same, because of small size and comparatively higher electronegativity than the rest of the members. And one more thing, all of the first member of these groups or other groups have comparatively less coordination number. That means these type of elements will form comparatively less number of bonds than the other. For example, if you compare the fluorine and chlorine, then fluorine has only one bond formation tendency. That means its coordination number is only 1. Whereas for chlorine, you can get up to 7. That means chlorine can form up to 7 bonds. Now next, point of similarities between lithium and magnesium. As mentioned earlier, they have diagonal relationship. So what is the similarities? So similarity between the lithium and magnesium is particularly striking and arises because of their similar sizes, atomic radiuses. As discussed earlier, main reason is they have similar sizes. So lithium has 152 pm, whereas Mg is 160 pm, and ionic radiuses of both lithium plus forms 76 pm and Mg2 plus gives 72 pm. Normal oxidation state of lithium is +1, whereas for Mg it is +2. Magnesium shows +2 oxidation state. So main points of similarities are both lithium and magnesiums are harder and lighter than the other elements in the respective groups. Lithium and magnesium react slowly with the water. Their oxides and hydroxides are much less soluble, and their hydroxides decomposes on heating. Both forms nitride Li3N and Mg3N2 by direct combination with nitrogen. The oxides Li2O and MgO do not combine with excess oxygen to give any superoxides. The carbonates of lithium and magnesium decomposes easily on heating to form the oxides and carbon dioxide. Solid hydrogen carbonates are not formed by the lithium and magnesium. Both LiCl and MgCl2 are soluble in ethanol, and both LiCl and MgCl2 are deliquescent and crystallizes form aqueous solution as hydrate. LiCl 2H2O and MgCl2 8H2O. So both of them are moisture absorbing compounds. Now we will discuss about the important compounds of the group members. So first is some important compounds of sodium. Industrially important compounds of sodium include sodium carbonate, sodium hydroxide, sodium chloride and sodium bicarbonate. The large scale production of these compounds and their uses are described below. So first is sodium carbonate, or commonly known as washing soda. Sodium carbonate is generally prepared by the solvery process. In this process, advantage is taken of the low solubility of sodium hydrogen carbonate, whereby it gets precipitated in the reaction of sodium chloride with ammonium hydrogen carbonate. The latter is prepared by the passing carbon dioxide to a concentrated solution of sodium chloride saturated with the ammonia, where ammonium carbonate followed by ammonium hydrogen carbonate are formed. The equation for the complete process is as shown here. So ammonia with water and carbon dioxide, it forms ammonium carbonate. Ammonium carbonate with more water and carbon dioxide forms ammonium hydrogen carbonate. And this ammonium hydrogen carbonate, when reacting with NaCl, it forms ammonium chloride and NaHCO3, that means bicarbonate. Sodium hydrogen carbonate crystal separates, and these are heated to give sodium carbonate. So simply by the heating process we can convert this compound into sodium carbonate. So when we heat it, we get carbon dioxide and water back. So we can use the produced compounds again for same type of reaction. So in this process, ammonia is recovered when the solution containing NH4Cl is treated with the CaOH twice. Calcium chloride is obtained as byproduct. So NH4Cl with CaOH twice gives ammonia, CaCl2 and H2O. It may be mentioned that here that solvery process cannot be extended to the manufacture of potassium carbonate, because potassium hydrogen carbonate is too soluble to be precipitated by the addition of the ammonium hydrogen carbonate to the saturated solution of potassium chloride. So remember, as mentioned earlier, sodium hydrogen carbonate is precipitated, and in this case potassium hydrogen carbonate is not precipitated or crystallizes. So we cannot use the same process for potassium compound. So uses of this compound: it is used in water softening, laundries and cleaning. It is used in manufacturing of glass, soap, borax and caustic soda. It is used in paper, paints and textile industry, and it is an important laboratory reagent both in qualitative and quantitative analysis. So second is one of the most used and well-known example or compound, sodium chloride. So most abundant source of sodium chloride is seawater, which contains 2.7 to 2.9% by mass of the salt. In tropical countries like India, common salt is generally obtained by the evaporation of seawater, and we are well aware of this process. Approximately 50 lakh tons of salts are produced annually in the India by solar evaporation. That means we will feel the water, salt water of the sea in open areas, and then eventually water will evaporate and salt will remain. So crude sodium chloride generally obtained by the crystallization of brine solution. Now brine solution is concentrated seawater. It contains sodium sulfate, calcium chloride and magnesium chloride as impurities. Calcium chloride and magnesium chloride are impurities because they are diliquescent. That means it will form liquid compound, or they are moisture absorbing. To obtain pure sodium chloride, the crude salt is dissolved in minimum amount of water and filtered to remove the insoluble impurities. The solution is then saturated with the hydrogen chloride gas. Crystals of the pure sodium chloride separate out. Calcium and magnesium chloride, being more soluble than the sodium chloride, remain in the solution. So sodium chloride melts at 1081 Kelvin. It has a solubility of 36 grams, in 100 gram of water. So it is very good solubility at 73 Kelvin temperature. The solubility does not increase appreciably with increase in temperature. So we will notice a minor difference in the solubility with increase in temperature, but it is not significant. So it is used as a common salt or table salt for the domestic purpose, and it is used for the preparation of Na2O2, NaOH and Na2CO3. So that means we use it for in food, and we can use it for the production of some more important compounds of sodium. Next one is sodium hydroxide or caustic soda. Sodium hydroxide is generally prepared by commercially by the electrolysis of sodium chloride in Kastner-Kellner cell. That means we are passing the electricity from the sodium chloride solution. A brine solution is electrolyzed using the mercury cathode and the carbon anode. Sodium metal discharged at the cathode combines with the mercury to form sodium amalgam, and chlorine gas is evolved at the anode. So the reaction is cathodic reaction is Na plus accepts electron with mercury and it forms sodium mercury amalgam, and anode chlorine gets oxidized and it forms Cl2 gas. So amalgam is treated with the water to give sodium hydroxide and hydrogen gas. So 2Na amalgam plus H2O gives NaOH, Hg and H2. Sodium hydroxide is white translucent solid. So it is a semi-transparent. It melts at 591 Kelvin. It is readily soluble in water to give a strong alkaline solution. And this reaction, that means dilution of NaOH, is also exothermic, so its solution will heat up. Crystals of sodium hydroxide are deliquescent, and the sodium hydroxide solution at the surface reacts with carbon dioxide in the atmosphere to form Na2CO3. So this compound is also moisture absorbing. So it is used in manufacturing of soap, paper, artificial silk and number of chemicals, in petroleum refining, in purification of bauxite, in textile industries for mercerizing cotton fabrics. So mercerizing is a type of treatment which increases the strength of the threads, and it also reduces the shrinkage. Then for the preparation of pure fats and oils and as a laboratory reagent. Next one is sodium hydrogen carbonate. So we already discussed about the preparation in the first example. Sodium hydrogen carbonate is known as baking soda because it decomposes on heating to generate bubbles of carbon dioxide. So because of that, it leaves hole in cake or pastries and making them light and fluffy. Sodium hydrogen carbonate is made by saturating the solution of the sodium carbonate with the carbon dioxide. So we already discussed this reaction in the first example. So the white crystalline powder of sodium hydrogen carbonate, being less soluble, gets separated out. So Na2CO3 with water and carbon dioxide gives NaHCO3. So sodium hydrogen carbonate is mild antiseptic for skin infection. It is used in fire extinguisher because it releases carbon dioxide. Next point, biological importance of sodium and potassium. So typical 70 kg man contains about the 90 grams of sodium and 170 grams of potassium, compared with only 5 grams of iron and 0.06 grams of copper. So these are the important metals for us. Sodium ions are found primarily on the outside of the cell, being located in the blood plasma and in the interstitial fluid which surrounded the cell. These ions participate in the transmission of the nerve signal, in the regulating the flow of water across the cell membranes, and in the transport of sugars and amino acids into cell. Sodium and potassium, although so similar chemically, differs quantitatively in their abilities to penetrate the cell membranes, in their transport mechanism and their efficiency to activate the enzymes. Thus, potassium ions are the most abundant cations with the cell fluid, where they activate many enzymes, participate in the oxidation of the glucose to produce ATP, adenosine triphosphate, and with the sodium are responsible for the transmission of nerve signals. So this is a very considerable variation in the concentration of sodium and potassium ions found on the opposite sides of the cell membranes. A typical example, in blood plasma, sodium is present to the extent of 143 millimoles per liter, whereas the potassium level is only 5 millimoles per liter within the red blood cell. This concentration changes to 10 millimoles for sodium and 105 millimoles for potassium. These ionic gradients demonstrate that a discriminatory mechanism called the sodium-potassium pump operates across the cell membrane, which consumes more than one-third of the ATP used by the resting animal, about 15 kilograms per 24 hours in resting human. In short, these first group metals are very important for us.